Okay, can hear more. Testing 1, 2. Can you hear me? Are we okay? Today classroom setup a bit weird. Study group. Like we are in the classroom without. All right, let me close all this stuff so it's easier. So I don't know what you're gonna do. Okay, never mind. Let's just pretend it didn't happen. Okay, so I see. You adjust now so the angle. You want to sit underneath, like, okay. So today we are gonna. So last week we finished Unit 1 already, and I gave you some work to do. So if there's any question you would like me to follow up on, you can always ask in the chat, and then I'll just look at it lah when I get to look at it. Okay. But today we're gonna start a bit on thermal physics, and I think we wait for as we wait for Mr. Kong to bring the notes, maybe we will review something from here. So last week we did momentum, right? And I asked you to try 170 and 171.
I remember you said like
yes.
Do 1.1 also.
Do 1.1 also. Okay. So let's quickly look at 170 and 171. So this one is a standard situation. If they never draw a diagram for you, you draw yourself, no? Okay, so you have P, and then this is 80 gram, this is 40 gram. Then they collide with each other, Before the collision, P is traveling at 6 meters per second. Q is at rest, so it's not moving. After collision, they stick together, big PQ, and travel on together. It's the speed of P and Q after collision. Find the speed.
Yeah, teacher.
Okay. If you don't know where you again. Okay, now you. I cannot really hear you.
Teacher. Teacher.
Yes.
May I ask what happened? Like why did the time suddenly just get swapped?
The other class got problem, so we have to move. Are you okay with the move in time?
Yeah, kind of okay.
That's all right. Okay. So we're gonna do some of the initial momentum. It's not ever you don't know where the handout is from. Go to the class note. I put dates in every single thing that I upload there. So you just follow the date. This one from last week one. And there is a huge lag. It's supposed to mirror my iPad. What mirror? Jeremy is like, oh, no, loading. Loading. Okay. So this is because the Wi-Fi here is a bit sus. All right, anyway, we're going to find the speed of PQ after collision. So we have initial momentum is equal to final momentum because they move together. And this one can always apply this in every single collision question. So before collide, momentum is mv, right? So you take the mass of P 80 gram times 6 meters per second. Q is not moving, so you can show 40 gram times 0 if you want to, or you just put 0. Then now P and Q move together, right? So if they move together, then this is the final speed that I want to find. So I put a label V there, and this will be 80 plus 40 gram times V. So this one is 0, okay? Gram and gram, the unit will cancel off. So 你没有 convert 也不用紧 for this case. 80 times 6 is 480, 120 V. So from here, you will get V as 4.0 meter per second. So momentum is equal to mv. Symbol is P. So sometimes we can even use P as a symbol to represent momentum. Okay. This is a qualitative statement, meaning, sorry, quantitative, meaning you do calculation. If we look at the second question, 171, this one is qualitative, meaning they ask you to use words to describe what is going on. So let's check it out. We have toy train P, and my train 0.50 kg, traveling at 3.0 meter per second. Collides with a stationary train of Q. You know why their question all the same one? They just change the object, they change the mass. Yes, welcome to IG. And then they stick together. Collide now, stick together. What's the velocity of the combined trains? I give you 3 minutes. We want to find the velocity of these combined trains. Again, we're looking for this V. It's a bit like the second train is just there, just chilling, and then gonna whack from the back by the first train. And they both move forward. If you have an exercise ball at home, you can try this activity with someone. This got all come. Until unless you need to go early, then let me know.
Okay.
Okay. Wow, DC. The Wi-Fi really not stable, then I'll use my phone. I don't have charging. For answer more, share in the chat, please. Yuri, what's your answer?
Yeah. I go flip to the picture.
Yuri, let Yuri come back.
What? Wait, I have no idea. Oh, yeah, there it is.
C. C.
Yeah.
C. Hmm. Anything wrong with my working? B or D? Well, let's get the number right first. Do you get 1 or do you get 1.5? Because after that, they move together, right? So whenever they move
Oh, okay,
together,
okay,
we
okay.
add, we consider them as one.
That is A.
This one is boat trains.
A.
So they move together, so we add the mass together. A. Okay, so we have 1 meter per second. And then got change direction, man. Cannot be that. It'll be very weird, right? If you collide onto something, and if it change direction, then there has to be a negative sign in front. So because this one here is positive, so this one is same direction as the 3.0 meter per second. Is 3.0 also positive? Okay. All right. So that was what we did. Then you did 1.1. Okay, now I need to go and crop. Okay, so 1.1 is around measurement, length, time, density, equations like density is mass over volume. So I'm going to have to pull the laptop towards me to crop some of those questions. But you can do it now. 1 sec. You do already not 1.1. 1.1, the first page. Yuri, after 1.1, what should we do?
Straight up jump to chapter.
Jump to?
Yeah, teacher. I remember we also did pressure there.
We did what?
Pressure.
Pressure. Oh, okay. Is there any interesting question you think you want to ask?
No.
Okay. Okay. So Unit 1 stuff is pretty standard, right? So we'll probably do a question or two, then later you can go find an answer for you to mark. So we have 5 athletes PQRST completing a race, compete in a race. They got different time. Which statement is correct? Okay, so whenever I see a statement like this, I think to myself, well, I need to find out who won first, right? So who won? Shortest time, no. Shortest time is P. So P1, and the next shortest time looks like T. So 22.20 minus 22.50 is 0.7.
Teacher, the
Okay.
answer.
Sorry?
I think the answer is A.
Yes, the answer is A. So this, I want to point out something. All this, the precision, meaning 它的 stopwatch 的小数点 is up to 2 decimal point. So whenever you write this out, let's say in paper 2, right, you also must write this in 2 decimal point. So even though the answer is 0.7, you shouldn't write your final answer as 0.7, it should be 0.70. There are small technicalities. Okay. 65. Mass of a measuring cylinder is 190 grams. This is M. This is the volume of the liquid. Total mass of the cylinder and the liquid. Mass of liquid. And they say they will lower 4 objects. So there are 4 different blocks, 1, 2, 3, and 4. And we will lower them into the liquid. Which object will float? What shall we do? For cylinder 190 grams. Then we pour some liquid into the cylinder. This liquid is 400 cm cube. And now the cylinder is 560 grams. And then after that, inside the same cylinder, I put in these 4 things. And then I ask you which one will float. So 1, 2, 3, 4. What's the information that we need to find first before we can conclude whether they float or not?
Density.
What should we compare? Density of who? Cylinder or the liquid?
Liquid.
Liquid, okay. So we're going to find the density of the liquid, which is the mass of the liquid, or 560 minus 190 divided by 400. So 560 minus 190, 0.925 gram per cm cube. Who float?
Then one and two, because the density is less than the because
0.925?
because it's less dense than the liquid, so yeah, it floats. And also that diagram shouldn't be insane foreshadowing.
Oh, foreshadowing. No, if I want to foreshadow, it will look something like this. I zoom in. So if I want to draw this on the liquid level, here's what it will look like. Number 1 is very less dense, so 它是一点点在里面罢了。Number 2 is almost as dense, so 一点点在外面罢了。Then number 3 and 4 is just here. Okay. So this one new objective question, maybe I said no. Or maybe next time you'll see this. So the reason why 1 will float more than 2 is because 1 is the least dense. Yeah. All right. Next. A micrometer screw gauge reads 0.02 meter when the jaws are fully closed. So this one is 0 error. 0 error meaning when the reading is supposed to be 0, it's not 0. And then when I measure the metal wire, I get this reading. So to find the true reading, I will take the reading that I have taken in the experiment and minus the 0 error. You learned this one before in science, right? So 0.56 minus 0.02. So if you think of all the objective questions that you have done for your, I don't know lah, for your school one is definitely more complicated. IG one, they seldom put trap one. They're very nice to students. Okay. And the last one, we are looking at wooden raft float on a lake. Okay, the density of the lake is 1,000 kg meter -3. The size of the raft is 0.2. Okay, this one is a square wooden raft. What is this in Malay already? Tie all the wood together.
But sama
Forgotten already, but name one. It's not a sampan. It's just a piece of wood. Okay lah, you get the point lah. It may come to me later.
rocket
Rocket ah, is it a rocket? Okay lah, I think so. Later we Google. So this rocket is 2.0 meter on each side. And the thickness of the rocket is about 20 cm. This is the mass of the rocket. How many barrels can I put on the raft before it sinks? I'm gonna load some. Yeah, I'll go nicer one. Let me think about it. What information do I need to find? This is my raft. I'm gonna put some barrels on top. Each barrel is 100 kg. How many barrels can I put before it starts to sink? 7 ah? So you want the density of the thing to be the same as the density of the water, right? You say that the density of the water will be equal to the density of the raft and barrel combo. So density of water is 1,000 kg per meter cube. So I know the raft itself is 700 kg. I don't know the mass of the barrel. I'm going to put M. This M is the total mass of the barrel. Mass. This M is all barrel. So how many meter cube does the raft occupy? So you're gonna go like 0.20 times 2.0 times 2.0. So as the volume of the raft.
the volume is 0.8.
Volume is 0.8 ah?
I mean the yeah, right, the volume.
Okay, so I times 0.8. Now I divide, wait. Then this is 700 plus M. So
Wait,
M
no,
is
how?
what?
Wait, no. How is it? How could it be? How could it be 0.8 meter cube when like how, man?
Sorry,
Wait,
you already saying again.
that's very suspicious. Like 2 times 2 is 4. 4 times 0.2 is straight up. 4 times 0.2 is already 0.8. What the? Like
No.
I feel like it's impossible.
4 times 0.2, not 0.8, man.
Yeah,
So
but
you can only fit one barrel. You want to fit more barrel, you need like more volume. The wood needs to be like
actually, to be honest, first I just checked just 700 divided 0.8 and then 700 divided 0.8 and then yeah, I get 875 and 875 for density and then like I just put 8, I guess.
Yeah, but very weird, right?
I have no idea what.
So this one is 1 barrel. Okay. So this one is a bit more K-bar, but either way, you want the density of the rock and density of the water to be the same. Okay. In fact, now we can move on. I'm gonna message Mr. Kong because how long does he need to print one stuff? Okay, now man. Okay, so we're gonna look at where was it? Here. My review. So we did this. Then we also did density, and we did some momentum and collision questions. So and then yes.
The pressure questions, have you discussed that already? Because I
No.
remember now.
So we'll discuss the pressure questions now. Let me fly there first. So pressure question. The first one you will see is this block, and they ask you which side will produce the smallest pressure. So you can think about pressure as force per unit area. So if I want smallest pressure, do I want largest or smallest area? Should my area be large or small? Just scroll all the way back. Some more. Belakang some more. Okay, there, in front of it. Okay, there we go. What do you think, Charlene? If we want a small pressure, should we take a large area or a small area?
For smallest pressure,
So we should take largest area or smallest area? Because pressure is force over area.
if the pressure is smaller, the area is larger.
Very good. We want a larger area. So we can find the largest area here. It looks like P to me. No need to calculate. You look at it, you know already. Right? Okay, moving on. A student calculate the pressure due to liquid at point X. Okay. And it takes 4 measurements: density, temperature T, depth of point X. So depth of point X below the surface of the liquid. You take from the surface here and you measure until the liquid. You call this H. The surface area of the liquid. Which measurement? Surface area, this area here. Which measurement must the student use in her pressure calculation? So this one is liquid pressure. The equation is rho Hg. So I guess we need 1 and 3. Density and the depth of the water. Now come to objective length. Okay, looking at the next one. This one, there is a stone suspended on the string. So you tie the string on the stone and then you dip into the liquid. Okay. The stone experiences a pressure caused by the liquid. So right on top of the stone here, there is a 水在压着它. So that's causing pressure. What would increase the pressure? decrease the surface area of the stone, increase the mass of the stone, lowering the stone deeper into the liquid, or using a liquid with lower density. Kindly vote your answers. Pressure of liquid, H, rho GH, rho HG. Yuri, what do you think? What's your answer?
A.
Yeah.
Because the same force with less surface area causes higher pressure.
How would you,
Teacher, is the answer C?
yes, the answer is C, but how would you make the surface area smaller? Let's think about Yuri's statement just now. Smaller area with the same force. But you see, if the stone is smaller, the water that is on top of the stone is less water, less forceful.
I know.
The water will what? I mean, the stone is not moving, 它只是绑着的。So in this case, the answer is C, because you increase your H. And then this one, the counter, or the reason why it doesn't work is, well, the most straightforward one is because pressure or liquid don't have area, but also because less surface area, less water mass or water weight on top of the stone. So because of this, the pressure is constant. P constant for same depth. So the only way to increase liquid pressure is to adjust the height or use a water of larger density. Change the water. All right, this is a mercury barometer, which is the atmospheric pressure. So remember, whenever you see a barometer, you're going to operate on the same principle, same depth, same pressure. So which side is exposed to the atmosphere? Here and here. Okay, so the pressure at this point is atmosphere. And it will be the same as the pressure at this point. So we are looking at this amount of mercury. Yeah.
B.
So the answer. Look carefully, B, the label. I want to measure from here to here. So the answer is C. Same height, same depth, same pressure. pHg. So the amount of mercury that is, the column that is pressing down is the length of C, because pressure of mercury is rho Hg. This one is density of mercury. This one is the height C. So this is used to measure the atmospheric pressure, because the atmosphere is this one. Okay. All right, next. We're given the density of mercury. What is the pressure of the bottom of a column of mercury at a height of 75 cm? So this question is actually identical to the one on top, which is your atmospheric pressure. So if you know your atmospheric pressure, the answer is B. If you don't know, then you calculate. No? So P is equal to rho Hg, 13600. Height is 75 cm, 0.75. This is also the height of C. And this G, this is old question 2019. So 2019, we're going to use 10 because this is paper one. If not, maybe cannot find the exact answer. Because your year is the first year with new syllabus for physics lah. Not sure for other subjects. So 1.02 times 10 to the power of 5. Or I already know the atmospheric pressure. It is 5, 10 to the power of 5. Next, do you notice that this question is almost identical to the previous question? You read carefully. It's just that instead of 75 cm, they put 780 mm. And instead of 13600, they put 1.36 times 10 to the power of 4. Slightly higher. We are still looking at 10 to the power of 5. Because your working is the same one. 1.36 times 10 to the power of 4. This one is 0.780. This is 10. So 只是从0.75变0.78, everything is the same. So we should still stick to 10 to the power of 5. Just found every year one of these questions is very nice bonus. Yeah. All right. Slightly less bonus. I am now going to increase the atmospheric pressure. So if I think about P is rho Hg. So P increase. And we know H will increase. So which is the distance H that will increase? Now? Is it VW? Is A? Is it WY? XY? Or is it XZ? C, D, D. What the H 变大了. This is my H, right? So if H increase, which one should increase? The H is taller. Because pressure increase. Looks like D, right? Because if I want this part to be longer, what will inevitably happen is that this part extra also will be longer. So B. Okay. All right. Let's see. We got a lot of YouTube. Okay, you can see the end. I'm going to give you a minute or two to try the rest. I'm going to go downstairs and see if I can get the thermal physics notes. Go toilet, go. So try the rest of the question, and you really get to pick the next subtopic that we want to go to. Where shall we go?
Let me see.
1 point what? Question you finish already.
Ah, 1.5.
1.5. Okay. You do the question already. You can mark. I'll find the answer and write at the side. Hi. Oh, you pink color. Petrol. You went to the toilet? Yes. Mm. Your time. For him, because he's here. Mm. Okay.
This one.
Yeah, lor. What's the problem? You don't know how many I done, right? I can go down to you later if you. Because the year 10, year 11 got one more. Year 11 got one more document. No, like one more you didn't train. The objective. I can go down. I'll go down later. I'll go down later. Uh, Okay, I'm back. Anyway, answer is in the chat. You haven't do, then you copy first one, go back and try. Okay, I want to start the next unit now. So everything all pretty standard lah. I think you get the idea already. So go try out, and then if anything, we can spend maybe 20 minutes, half an hour just doing pressure questions next time. Copy answer. For the last few pages. And I'll put in chat. You finish your Zoom now? Yeah, my computer is very slow. Like me, just slow. Charlene, if you come back face to face next week, can you print the notes yourself? Or do you want Mr. Kong to print for you? Yeah, you print yourself lah, because I think a bit mafan him also. Thank you. It's the no printer, right? Okay, so I'm gonna send the link to today's notes for you. Second. Let me see. So as usual, the pages that you will see, they come from the textbook. So if you want, the textbook is all in Google Drive, okay? A soft copy of it. I'm trying to find is a hard copy or a soft copy of the more recent textbook. See that, still digging. Yeah. Okay. So go try out. Then you already say want to do 1.7 work energy power.
Oh, I said 1.5.
You say 1.5
Yeah, I said 1.5.
I must be dreaming. My wow, yeah, don't remember. Okay, so if you want to look at 1.5, let's try to find this. Yes. No, this turning one, turn one. Okay, I'll do one question. Then you can do the rest yourself. Then we'll look at it next week. Yes. Huh?
107.
Do 107. Okay. 10. 107. In 1.5.
Yeah.
Okay. So we're going to do 1.5, and it's mainly about movement and turning effect. So if you look at 107, we'll give Jeremy a minute or two to find the question. One under subtopic 1.5. A beam of 6 Newton suspended from 2 strings, P and Q. Where is Q? Wow, Q is not shown. Very good, very nice. So we have string P here, and then there's a tension of 2 Newton. And this beam is 6 Newton weight downwards, and it's pulling down, I guess, at the 20 cm mark. Okay. What is the tension in string Q? Let's say this is T, TQ. And where should I put it so that the beam is in equilibrium? Okay, I guess the first thing is I need to choose a reference point or a pivot. And the easiest point to choose is here. Because I know the distance from this point now. They label so nicely 了，我不用都是浪费了 correct? This one is 90 degree. And this 6 Newton, let me change color a bit. This 6 Newton will cause it to turn clockwise, correct? So I would say the clockwise moment will be equal to this 2 Newton will cause it to turn counterclockwise. If this is equilibrium. We know there is not equilibrium because there is still the string Q that but what I know is I maybe need to calculate and see which force, which torque is bigger, the green color clockwise torque or the blue color anti-clockwise torque. Which torque is bigger? Then I know which other where to put my string. So this is 6.0. 20 cm is 0.2. Or I guess you can keep your 20 cm if you want to. Now I change 0.2. Okay. And anti-clockwise here is 2 Newton, 2.0, multiplied by 0.3. So on this side, I have 1.2. And on the other side, I will have 0.6. Who needs help? Looks like anti-clockwise 不够用，对不对? So I need to add the torque due to string Q here. Because the 6 Newton can give 1.2 Newton meter. But the 2 Newton only give 0.6. So 2 Newton 是不够4的. So the torque of Q is 0.6. That's what I know so far. So now I have a few options because objective question. So I want to find which one is not 0.6. So to find torque of Q, I will take 4.0. And then they measure all of this from the left-hand side. Oh, very nice. They also use the same point as a pivot. Let's say this is point, I don't know, point X. They also use this point X as a pivot. Left hand, left hand, left hand, left hand. So I can just multiply 0.10. So this is definitely out there, 0.4. A is out. 4.0 times 0.15 is 0.6. So this is maybe. 6.0 times 0.10 is 0.6. So this is maybe. 8.0 times 7.5 cm, 0.075. How much is this? 8 times. Wow, also 0.6. So we can eliminate A, but now we are left with B, C, and D. So I have to figure out, because this TQ is 0.6 and also it is anti-clockwise. Because it's on the anti-clockwise side, correct? Right, so I know TQ is 0.6. I also know it is anti-clockwise. So which one is anti-clockwise? I need to draw them. No? If it's 15 cm from the left-hand end, 15 cm is 大概这边. This one is clockwise. So B is out already because B is clockwise. Correct? 10 cm. Where is 10 cm? From the left side. Well, even closer here. This is also clockwise, right? So you have option C here. You have option B here. These are all clockwise, so out there.
D is also clockwise. I feel like D is also clockwise because 7.5 is also like just about like because it's also at the left side and it's more.
So 7.5 is here. So it looks like everybody is clockwise, or then how go home? How?
Therefore D isn't the question. Therefore D, I don't think so.
No, cannot therefore D. You
Then
eliminate.
how?
Then how? Do you notice there's a problem with the way of me drawing the force? Should I have drawn the force upward or downward?
Yeah, should about be upwards.
Because it's a string, right?
Yeah, it's a string. And you have no idea, and like, well, it's suspended, so
it's
you can't just let it dangle like on the beam. You can't
Yeah,
on the
like you dangle like that. What nonsense! Somebody should have said something nice. 这个是绳子，挂着的绳子
They said
must hang
suspended.
suspended. So you have this. Okay, let me label the forces. You have this, which is midway 6 Newton here, or 8 Newton here, or 4 Newton here.
Oh yeah, because 8 Newton at the most further most further, so it like feels like it can pull better.
No nonsense like that one, never like that one. So you gotta ask yourself, right? Okay. Just think about it. If I want equilibrium, the torque have to be the same, but what else have to be the same? Something else have to balance one. What is that something else? What do you think? Let's draw. Let me draw a bit more accurate. Because there are two conditions for equilibrium. So here is 4 Newton. Here is 6 Newton. And here is 8 Newton. Which one should I choose? What do you think, Jeremy? So that are balanced. It won't accelerate up. It won't accelerate down. The forces are balanced. In 6.0. Okay, maybe I'll draw the beam outside. Okay. See the beam like this? I have a string here, I have a string here. This string is 2.0 Newton. The weight is 6.0 Newton. What should be the other force? Yeah, 4. So the answer is B. Why? Think too far away already, you already? They cheated your feelings. It's okay. So the difficult one is actually finding the torque, okay? But the easy part is actually to know that you need 4 Newton. So if you already know that you need 4 Newton, C and D is an automatic wrong. Yeah. All right. So you only have A and B. And between A and B, only B will give you the clockwise moment of 0.6 that you are looking for. I mean, so the anti-clockwise moment of 0.6 that you're looking for. Okay. So whenever you see equilibrium, there are two conditions. Number one, net torque is 0, which we are very fast to use. So clockwise is equal to anti-clockwise. And the second one would be net force is 0. Okay, so the upward force is equal to your downward force. Or left is equal to right. But in this case, there's no left and right. Right. Have fun with the other questions. I'll give you answers next time, then we can check them together. Do you need another pen? Just open only. This pen. Got warranty or not? Okay. Never mind. We're going to look at the next unit. Unit 2. Unit 2 is quite nice. This is about thermal physics. And thermal physics is basically, we're going to look at the particles. So I'll give you an overview about the chapter, then we can start. So all this I take from the Stephen Popple. So for thermophysics, there are three main things that we are going to cover. Okay. The main idea of thermophysics is that we have this thing called heat. You heard of this term before? Okay, so symbol 我们通常用是 Q or big Q 啦。Okay, and for this heat, it is a type of energy ma. So the unit is joule, J. So what we are going to concern ourselves in this chapter is, number one, we're going to look at the effects of heat on solid, liquid, and gas. So heating, solid, liquid, gas. This is like science 101 now. When you draw all the atoms very close together, very far apart, when you heat them, what happens? Okay. So the second thing we're going to look at is when we heat this solid, liquid, and gas, we need to be able to measure temperature. So how do we measure temperature? So we're going to look at some thermometers. And then after that, we're going to move on to look at how do we calculate heat? Calculate the amount of heat transfer. Because remember, the whole idea is we're going to heat from solid. Everyone know how to draw this diagram, right? From solid to liquid. There's no fixed shape. To gas. So in this process, you must keep adding heat to the system, right? So we're going to calculate how much heat is being transferred. So the idea is around calculating the heat transfer. And then after that, number 4, the final part, because in my brain, I actually see number 2 and 3 as the same thing, but I guess I'll just separate them. And the last part we're going to look at is heat transfer. What kind of material has better heat transfer compared to others? And that's the whole chapter. Okay, we're going to start with the first one. What happens when we heat solid or liquid or gas?
Wait. I'm still copying.
Yuroi. You attend my class long enough, you know I will keep bringing you back here and filling in all the empty spots, right? You copy make sure you got empty spots. Or you have this map in your brain, it's mainly for your brain. So that 你知道你在哪里啊，不然的话你就好像教完了啊，还没有教完啊，有这个 topic 咩？ So it give you like a big picture view like that. Like you go for, like you say you go Disneyland, you go and watch it, look at the map.
Okay.
Okay, thanks, Yuri. So just chill a bit, and we're going to look at some iceberg. What is the giant iceberg? Insert global warming? I don't know. So we know water can exist in 3 states, right? There's solid, there's liquid, there's gas. And the first thing we need to talk about is using this idea called kinetic theory. Okay, so this is used to explain how solid, liquid, and gases behave. All right, so kinetic theory 好像很 fancy 这样, but it's actually very normal. This theory says that matter is made out of tiny particles, like atoms or molecules, and then they keep moving. So for example, in solid, the particles will vibrate about a fixed point. So currently, if you are using a table, the particles of the table is actually vibrating. Okay, no, you don't feel it, but it's vibrating. Okay, so what we're going to do is we're going to learn the terms to use to describe this. So for solid, it has a fixed shape and volume, and the particles are held closely together by bonds. So in chemistry, you learn bonds, but now in physics, we 全部都是叫 bond, okay? Van der Waals, ionic, covalent, 全部是 bond, okay? They vibrate backward and forward and cannot change position. Like you during the perhimpunan time. You sit in your neat little row and you just sit there and clap hand.
I disagree. I drink water.
Or you can change position. You pengawas, is it?
No lah,
Can walk
no lah.
around.
I can just sit there and drink water and like move my legs or whatever. Oh wait, yeah, that also counts as vibrating. Never mind.
Okay, so then we move on to liquid. So liquid have a fixed volume, but no fixed shape. Okay, so it will follow the shape of the container. Particles are still close together, and then they still attract each other. But because they vibrate so much, right, the attraction cannot hold them in fixed position. So they can slide and move past each other. This is like you during recess time. Your school, a lot of people want, correct? So during recess time is 人山人海. Hello. It's normal for you to walk through the canteen. Then you gonna bump here, you gonna bump there. Then you're like, excuse me. Normal lah, this one. So liquid. You in canteen. Can?
Sitting and then the one just banging like that.
Oh yeah lah. And then they are so blur, they won't say sorry one because they don't know they bang. Like, dude. You know? So cannot hold them in fixed position. They will move past or slide past each other. Okay, next, gas. This is your school at 6 a.m. Some people come super early. I don't know why. Maybe transport problem. Or when you come to school at 6 a.m., got people or not know, maybe you and a few other jokers, then you just hide or just sleepwalk around. So gas has no fixed shape or volume. It will quickly fill any space available. So if you are a if you are the quiet, introverted kind of person and you go into let's say you go into a classroom, you're not going to stick yourself very close to this random classmate that you're not very close to, right? The most you say hi, and then you go sit at your corner, then you're going to go sit at that corner. So they all will stay far apart one. The particles are well spaced out and virtually free of any attraction. So there's no bond or very little bond. But the only difference between that and you is if they are moving at high speed, colliding with each other and the walls of the container. Okay, so we're going to summarize this a bit later, I'll write it down. But at the end of the day, right, just so you know, the particles that we talk about in physics, it can be atoms, it can be molecules. But because we are learning physics, so we are not going to specify whether it's atom or molecules, we just keep calling particles. But when you're studying chemistry, it is important for you to know, for example, if I say water, it is not water atom, but water molecule. If it's iron, it's iron atom, not iron molecule. But, well, back to physics. Okay, so this is the kinetic theory. And one thing that is interesting is this thing called Brownian motion, which shows us the motion of the particles, especially that high speed, this one, high speed colliding with each other. So we can see this using Brownian motion. I'm pretty sure you have heard of this before. And to see Brownian motion, what we need to do is we need to install a microscope, and then we put some smoke inside here. Put some smoke here. So when I was in high school, I used to come from a very gangster school, so quite a few of my classmates smoke one. So my science teacher just asked one of them to give her one of their cigarettes, and then she burned it, and then she put the smoke inside in the smoke cell, and we shine a light, and then you can view it through a microscope. So what you see in microscope is the zigzag pattern of the smoke particle, because smoke particle is carbon， 它是一粒一粒很小的 carbon， 黑黑的嘛。那个 carbon 撞到 oxygen 撞到 nitrogen 它就会反弹。So then you get this kind of zigzag motion. The particle 走下撞到一个 oxygen， 撞到一个 nitrogen， 撞到一个 oxygen， We're just colliding and then 一直换位。But like you lost in some place there. Okay, so this part here, the whole idea is that there is zigzag motion. Okay, and you see the smoke particles. If you don't have this atas setup, you can still see Brownian motion. If you take a very dusty pillow or a dusty soft toy or a dusty carpet, and then you wait for the sun to come in early in the day or evening, and then you whack, and then you see the dust fly out. And then if you stare at one or two particles, you will see that they change direction. Okay, so these particles are actually moving, and because they are moving, right, we say that they have kinetic energy. Even solid also have kinetic energy because they vibrate, correct? And they also have potential energy because their motion keeps them separated and opposes the bond that's trying to pull them together. Okay, so particles in gas have the most potential energy because they are furthest apart. So just a reminder, based on what we've learned before in Unit 1, kinetic energy is the energy because the particle is moving. And potential energy is because of the change in position or shape. So when the particle move apart, there is more potential energy. You can see something like this. So let's say this is solid and the particles are close together. So it's like a spring. And then what happens when you stretch the spring? You stretch the spring. You store more and more potential energy. So from here to here, potential energy increase. Okay, so this spring is to represent the bond. This is solid, liquid, and gas. Okay, so the thing about this chapter is that we are going to use this understanding to look at the heat transfer, because we want to talk about the energy of the particles, and this is internal energy, which is the kinetic energy and the potential energy. The hotter the material is, the faster the particle move, the more internal energy there is. So this one, probably some science teacher also told you before, when you heat particles, they vibrate more until they vibrate so hard, they separate, become liquid. And then they vibrate some more until they vibrate so hard, they go further apart and become gas. So this idea is such that if a hot material is in contact with a cold material, the hot one will cool down and lose internal energy. Okay, so this energy transfer is known as heat. So this is the whole focus of this chapter. We're going to look at the thermal energy and also the energy transfer. All right. So I'm going to summarize or basically draw this table that you have seen like many times before. Do you think? Oh, cannot. No, that's a bit sad. Never mind. So I'm going to draw the comparison between solid, liquid, and gas for you. And in the meantime, because I don't have double screen, we will do a question. Beautiful. Half of this is the bullet. Okay, so in the handout, we're going to look at number 83. Yes, number 83. In page 436. What page number? 6.
Teacher, just A and B hor.
Well, if you feel like it, you can do C, yeah. We have done C before. Mhm. Okay, we'll discuss the question now. Anyway, give me a sec to paste a screenshot here. Because look, you want to copy everything I dump into, Google Drive. Don't worry, you're not missing out on anything. But I'll put the screenshot there. Okay, don't worry. Okay, so what we've done so far is the basic stuff, like the shape, the volume. And the important one is the multicolor one, because in physics, what we care about is less of the volume and shape, but more about the energy situation. So as you go from solid to liquid to gas, so from solid to gas, the bond goes from strong to weak. That's why the potential energy increased, and the kinetic energy also increased because you went from vibrating at a fixed position, at fixed point, to moving freely in gas, colliding with each other and the container of the wall. Since internal energy is the total of Ke plus Pe, you got Pe here, you got Ke here, then if both Ke and Pe increase, the internal energy also increase. So in the next lesson, we're going to talk about what happens when we add heat to the system to increase the internal energy, which is essentially heat transfer, melting, and boiling. All right. We're going to look at the question that I asked you to try, which is page 4. Okay, this one. Right, the circle represents molecules in different state of matter. Identify A, B, and C. If you cannot identify, then sorry, but hopefully it's pretty straightforward. C is gas, right? B is solid, and A is liquid. Right, bonus question. Explain in terms of forces between the molecules. So forces between the molecules here is about bond. Okay, why gas expand more than liquid when they have the same rise in temperature, assuming that the pressure remains constant? So I think first thing we want to do is we want to compare the bond between gas and liquid. Which one has a stronger bond? Gas or liquid? Sorry? Yeah. So forces between molecules are stronger in liquid. Hence, liquid expands less compared to gas.
Teacher, can I talk about gases instead of liquids?
You can talk about gases instead of liquid, of course. As long as 那个 idea 在那边就对了。In fact, I would say that the bonds between bonds between gas particles, the forces between gas particles are very weak. That will be an additional point.
Teacher.
Yes.
I'd rather say that forces between gas molecules are weaker than molecules in forces between liquid molecules. I mean forces between gas molecules. Huh?
Can, no problem. As long as you compare them, this is not SPM. So they're pretty chill. As long as you compare them appropriately, can already. But I shall okay. Moving on to the next one. Anyway, I just want to double check and see how particular they are in the mark scheme. I don't think they will be, but just in case lah. Who knows? If you think Cambridge is a more consistent syllabus, unfortunately they are not. But SPM is way more consistent. Because Malaysian people must follow the law one, especially your teachers who mark paper. Okay, so that's fairly recent. Winter 2023. So the marks are given if you say that the attractive force is bigger, and also, so if you compare one enough already. So mine is fine if you say that it's very weak or zero, or you say it's lower than liquid can already. Okay. And then the second one that you could also mention, I didn't say, which is the average distance. Because the particles are closer in liquid, right? That will be the last point. The average distance between the gas molecules are greater. Because the main idea here is that if the particles are further apart, and then you make them even more further apart, then the expansion is more. Meaning, if let's say gas, it was 0.1, it's easy to go to 0.2. Whereas for liquid, it may be 0.001. So if you want to go from 0.001 to maybe 0. You want to compare right here to here, we add, I'm just showing you the percentage increase. So here to here, we add 50%, right? But if I want this to match 0.02, I need to add a few 100%. So that's what they're saying. Average distance between gas molecules are greater. All right. So I think we'll stop here. But in case you're wondering this one how to do, this one is your P1 V1 is P2 V2. Try out the equation. The whole idea that pressure and volume is inversely proportional. So if pressure divide by 2, P become P over 2, then V over 2 will become V. Okay. All right, we've done this before. Go try some. I'll see you next week. Same time, same place. If you're coming, you go and print out your own notes, okay? Take care. Bye-bye. So nothing much done. You go and review the top question on your own, and if you want to, you can try. You can just finish up part C. We'll continue with this. There's nothing much here that I feel that you need to know besides the kinetic theory. Bye-bye.